The next presentation is by Mycronic. The speaker is Romain Roux, and he is going to be speaking on deep learning AI. 1 year ago, Mycronic, D2S, and NewFlare decided to create the Center for Deep Learning and Electronic Manufacturing. They came together to pool talent and resources to advance the state-of-the-art in deep learning for their unique problem space and accelerate the adoption of deep learning in each of their company's products to improve the respective offerings for their customers. Romain?
Good afternoon, and thank you for the introduction. Very excited, a bit nervous, I have to admit, to give this talk. It may be a bit unusual, I think, for two reasons. First, I'm not used to give this kind of speech, but also I'm not at all familiar with all high-level concepts of Industry 4.0. I'm more of an R&D guy, working for 15 years on computer vision, and like lots of others, I started to look into deep learning to solve some of the problems we encountered. So I will start with a brief description of my company, and I will switch to what is machine learning, where deep learning fits into this description, and show some nice applications of deep learning and how we can help us to go toward a smart factory, the so-called. So Mycronic has two main businesses. The first one is pattern generators. So Mycronic is by far the leaders in mask writers for the flat panel industry. We also have another business, which is the assembly solution, and I will talk a bit more about that industry in my talk. So Mycronic assembly solution has 4 branches: surface-mounted technology with pick-and-place gel printing and tower for material handling. And we also have inspection division for the SMT with SPI, NOI, and also a web-based software for process line control and real-time review. We're also offering a dispensing solution and assembly automation for the automatic assembly of cameras for the automotive industry, especially, and die bonding. So, at Mycronic, we are, amongst other things, we are focusing on the so-called batch size 1. We want to enable that. So our goal is to get the fastest and most reliable possible programming of each machine line, so we can start producing a new product with the highest FPY possible. We also want to have this shortest fine-tuning phase. And we don't want to babysit the machines on the line, you know. So we want to reach the stable production as fast as possible and ending with the highest FPY possible. So, yeah, and also another part of the equation is the maintenance scheduling. We don't want only program regularly maintenance. We want the maintenance to be scheduled based on indicators that the health of the systems is in a state that requires corrective actions. So to achieve these goals, we believed at Mycronic that deep learning can help. So we decided, 1 year ago to join forces with D2S and NewFlare, Digital to Silicon and NewFlare, because we believe that together we can actually speed up the time to market of deep learning in our industry. So at the CDLE, the Center for Deep Learning in Electronic Manufacturing, which is located in San Jose, the staff is composed of experts in deep learning, but also short-term and long-term assignees from each company that are joining the CDLE for a period from 3 months to 2 years. And I am actually the long-term assignee of Mycronic, so for 2 years in San Jose. We have 2 goals at the CDLE. The first one is to quickly help each company to build deep learning applications for the product, and a long-term goal, which is more about providing a training about state-of-the-art architectures in deep learning and help the companies to be autonomous in deploying such applications. And the past year confirmed that it was a good choice because we already achieved 10 successful projects, both in the flat panel industry, semiconductor industry, but also in SMT. But now we are going to switch to the technical part of the talk about machine learning and what is machine learning and where deep learning is into that description. So machine learning can be defined as the study of systems that are able to improve their behaviors based on experience. So if we rephrase that sentence, this is the study of algorithms or programs that are able to tune, to change their internal parameters to get better at their job. And how they do that? By looking at data or interacting with an environment. So there are three types of learning: supervised learning, unsupervised, and reinforcement learning. Supervised learning, this is the most common case. You want to create a model, this function, mathematical function, that is trying to transform an input into an output. And you have a database of input and corresponding output that describe the behavior you expect of your program, from your program. Unsupervised learning means that you don't have this output. You just have input data. And we'll see later on that it's still very useful. And the third type of learning is called reinforcement learning. I think we'll have a talk tomorrow from Uber AI on these topics. Looking forward to hearing that. Here, we don't have a database. We have an environment. And our model will interact with the environment by performing actions and getting a feedback from the environment, observation and reward. And the agent has to be trained to maximize the probability of getting a reward. So it may be still a bit fuzzy. So let's take an example. Imagine that you have color images of a board with solder paste on it. And you want to create a program that is able to identify which pixels are paste and which pixels are not paste. So you could start by describing what paste looks like. It's grayish, right? It has a specific texture. So you could start by creating these rules. And this is called rule-based approach that has been used for decades now. Or you could try to use supervised learning to do that. If you have a database of corresponding color images and this segmentation, image you can see on the bottom right of the slide, then you can start to train a model. And I'm not saying anything about the model yet. You can feed the color images to your model. It will compute an output. And at first, without being trained, the result will be completely useless. But if you compare, you compute the error of your model by comparing with the output from your database. You can actually update the model. So the next time your model encounters the same image, it will be better. The result will be, the error will be slightly smaller. And you can iterate that process until convergence. Unsupervised learning. So unlabeled data is definitely still very valuable. This example is the framework is almost similar to supervised learning, except that when you are computing the error, you are not using any ground truth, the output from the database. Here, this example is called the autoencoder. So the autoencoder is composed of two functions, an encoder and a decoder. You can see that basically as a compression and decompression. Here, what we are trying to do, the encoder, the first part of the function, will try to compress the data, giving you a smaller representation of your data. Here, it's an image, but it can be any other type of data. And the decoder will try to do the opposite job, reconstructing the image from the smaller representation, which is called a code here. Both encoder and decoder will be trained at the same time. And well, at first, as for supervised learning, they will do a very bad job at it, but after being trained, they will get better and better and specialized to compressing and decompressing this type of data. So if you are feeding the networks, only the models, only with images of components, they will be very, very good at compressing the data, the images of components. But they will be very bad at reconstructing other images. And we'll see how we can use that to perform anomaly detection. In a few slides. So, the model itself, well, I guess you know that I was talking about. why deep learning, why deep neural networks are so popular lately. So deep neural networks are a kind of model you can use in machine learning. So deep neural networks, they are composed of a sequence of very basic mathematical operation. Convolution, which is basically filtering, sum, multiplication, and that's it. It's very simple model, but you can sequence lots and lots and lots of this operation. Each of these operations, they have a few parameters, and yeah, by changing the values of this parameter, you can completely change the function performed by these networks. So they are very, very flexible. This one is called VGG16. It contains 138 million of parameters. So you can do lots and lots of things with such huge amount of parameters. There is no formal proof that deep neural networks converge, but they do converge. That's for sure. And they are very computationally effective with the rise of GPUs, but also the storage and yeah, cloud computing and everything. It enabled deep learning to be used. And yeah, there is a general question about machine learning. How can we know that the neural networks didn't just learn the data from the database, but it's able to generalize to unseen data? And this is done using, usually we divide our database into 3 parts. One part for the training, and the one part for the validation. It's used as well for monitoring the training, and the last part is used for testing. So this test part has never been seen during the training by the network. So this is how we know that we can handle unseen data. And that's pretty much what I'm going to say about deep neural network, but I hope you will remember that they are not complex model at all. It's very simple. Mathematically, it's very simple. But they are very powerful. And I'm showing that here. So the first task, all of these examples are using real images from our machine. And the result I'm going to show here are real results of deep neural network. So the first task deep neural network have been very good at is classification of images. And for 15 years, they have been state-of-the-art for that task, achieving superhuman performance. Here, the idea is that we use a neural network to classify components. So to identify which package the component belongs to. So these are the actual image that we were using. And if you can see, some of these images, they contain other components. But still, the network was able to know that it should focus on the component in the center. It was able to achieve very, very nice accuracy. Another example of image classification is on the pick-and-place machine. I guess you know that. We have reels of component. There will be a tool picking up a component and placing on the PCB. But on its way from the reels to the PCB, we are taking an image of the component to check that everything is right. The component was well picked. It's not damaged, and so on. So here there is as well an application for image classification. And the result as well is outperform completely rule-based approach. Standard computer vision. Well, I already talked about the image segmentation, but definitely deep learning is very good at that. And the amount of images, we usually, when we talk about deep learning, say that we need millions of images. Well, definitely this is not true. Depending on the complexity of the tasks you want to achieve, a few images may be enough. And yeah, page segmentation is one of these applications. Another very nice application of image segmentation. Here you have the input of the deep neural network and the output. And this is the actual result of the image segmentation. So here we were able to identify which pixels belong to the body of the components, which pixel belongs to the leads, and which pixel belongs to the background. So with that feature, we are actually able to do automatic programming of the inspection, the AOI, the component inspection machine. Once you know where the body is, you know where to perform a coplanarity measurement of the component regarding the PCB to check that they are coplanar. You can check for lifted leads. You can put inspection area at the tip of the lead to check for solder joint. Everything is so much simpler once you have this geometric description. Another very nice application of deep learning is for domain transform. You may have heard about these deep fakes that deep learning enabled. Well, here we can use similar approach, which are called generative adversarial networks, GANs, to actually transform images from one domain to another. Here we were able to transform CAD images that just shows a label of an index of the type of component we are looking at to a realistically looking image. We can do the same to go from color images to depth map. And a neural network was able to transform this image that way. Definitely, it's out of reach of rule-based approaches, this kind of transform. How can we use that? Well, we can use that to generate unlimited amount of data to test our algorithm, even to train other networks on that. For instance, we can create, because it's easy to have normal data, right? Normal looking images, but it's more costly to have error on the PCB. So with that kind of generator, we can actually generate defects and check that our algorithms are able to detect that unlimited amount of data that way. So if you recall a few slides before, I talked about the autoencoder. And it can be used for anomaly detection because the autoencoder has been trained on normal cases. You have data from your machine, and you train an autoencoder on this data. If at some point there is abnormal, unusual, I would say, sensor data, your autoencoder will fail to reconstruct this data accurately. So by checking the difference between the input and output of this autoencoder, you can actually detect that there is an abnormal, an unusual behavior of your system. And yes, predictive maintenance, we already talked about it this morning. It's usually divided into different tasks, estimating the remaining useful life of your system, and estimating the probability of having a failure in the next time window. And deep learning are very good as well for analyzing sequence of data. So you could actually, at each point, at each moment, estimate the probability of having a failure in your system. And then you can actually not perform corrective actions regularly, maintenance operation, but you can actually schedule it when it's necessary, when the probability is higher than a certain threshold. The nice thing about it is that you can actually test corrective action. If you see that the probability of having a failure is dropping, you know the corrective action you took is the good one. Otherwise, you can test other actions. So we'll see. Now, we have a few building blocks, and what can we do with it to enable this smart factory? Well, let's go to the basic, the data itself. At first, we have measurements, and accurate, repeatable, reproducible measurements have been on the market for a decade at least. Here we are. I'm just showing that solder paste and AOI machine, they are using different kind of technology, but they are very repeatable and reproducible. Here, at this stage, definitely deep learning can do a lot. I mean, these are complex optical systems, and for modeling such a system, deep learning is very good. I won't go into detail about it. But there are a lot of algorithmic to transform the basic signal you have into a 3D reconstruction. Of course, deep learning can help on that. Then on top of measurement, you have the first layer of abstraction, the inspection. This is where you have CAD import, line review. This is where you can start having closed loop. So from the SPI to the printer, repair loop, from the SPI to the jet printing machine, My300 for Mycronic, that can actually add paste where there is insufficient paste detected by the SPI. You can also forward loop when the SPI is feeding the pick and place with measurements. So you can actually do not put the components on the copper pads, but actually on the paste. And we all know that it increases the FP wire of the line as well. And here we ask for inspection. Definitely, I mean, if you have labeled data showing which component is defective, you can actually use deep learning as well. It's basic image classification. That's one of the example here. Then on top of inspection, you have the system process control. And at the Mycronic, we are using the Sigma-Link software to do that, to have a real-time control of the inspection equipment. Sigma-Link provide high-level understanding of the process. You can perform, of course, CAD import on that, and also do the defect correlation. And here, you can start having the anomaly detection I was talking about before, because you can see, for instance, the SPI machine as a collection of sensors measuring volume, area, offsets of deposits. So you can start looking for anomaly, signature of the process that is anomalous. And natural extension of SPC, because, well, detecting a failure is okay, but preventing it is better. And here, I already talked about that, but this predictive maintenance I was talking about, you can use that directly on in a SPC. Because, well, you can see small deviation in the process, and you know something you will go beyond the tolerances at some point. So you can start predicting it and perform some corrective action, and for instance, printer maintenance when it's necessary. And yes, the last step is, okay, it's nice to have a human, an operator, performing this corrective action, but that could be good to have a system that is automatically, in a real time, compensate for this small deviation. And yeah, definitely the framework of reinforcement learning can be used to that. There is one problem is that they are very hungry for data. Just for the Go game, I guess you heard a few years ago, it was used to beat the Go world champion, and it generated a few millions of images. We don't want to waste a few million PCB to train such a agent. So this is where definitely simulated environment can help, the so-called digital twin. So we are not there yet, definitely. So yeah, Mycronics is investing a lot in deep learning. We believe it will get us, and this is one amongst many other initiatives around Industry 4.0. If you want to know more about Mycronic and the CDLE and about deep learning, feel free to contact me or Agile Barenwal, who is the director of the CDLE. And yeah, there will be some presentation of our products and AI-based functionalities at the Productronica in November, so don't hesitate to visit our booth. Thank you for your attention.